So it is an enormous pleasure for me to introduce Dr. Aleksandra Birn-Jeffery, also known as Ola. She completed her bachelor's degree at the University of Bristol and did her PhD at the Royal Veterinary College. And she did a postdoc over in California when I was doing my PhD, and that's how we met. It's been, I guess, 8 years or 9 years, I guess, that we've known each other now. So I am so happy to have an opportunity to introduce her. She works on neuromechanical control of movement, primarily using, or used to be primarily using bipedal birds as a model. But she's very interested in using those birds to then apply those neuromechanical insights to human locomotion and to learn something about how humans move, how humans avoid injury and falling. And we're going to hear a lot more about that today. So I'm very excited to have Ola here. So please take it away.
Perfect. Thank you very much. And thank you very much to Kathleen and Alessandro for inviting me to give this talk today as well. So what I really wanted to talk to you about today was some of the work I've done in the past and how that's kind of led to what I'm currently doing, and a few works that I'm still working on and we have some preliminary data for. But the general idea of the work that I do is removing complexity and seeing whether, if we simplify a system, whether that can give us just the same amount of information or even more so with regards to understanding control. So to begin with, I'm going to start, hopefully if it changes, screen. Why do we really care about understanding control in movement? What's the purpose for investigating or studying it? Well, we have a good understanding of how we move, both walking and running and other gaits within level terrain. But as we know from our daily lives, the outside world or even the inside world in our houses is not uniform. There's a lot of different terrain types or different obstacles to get up and over, and all of this involves complex behaviours. But it's not just the terrain itself that is complex. We have a huge amount of complexity within the way we can move as well, particularly some people more so than others as well, with the type of performances they're capable of doing. And most of these, the movement is what we would classify as not steady. It's not a constant steady movement. It changes and it varies all the time. And so in addition to the terrain complexity, we have movement complexity as well. What's interesting is that once we start looking at these unsteady behaviors or complex behaviors, it's where we start seeing performance limitations being reached. So whether it's an injury in a sharp stop or a tight turning radius, or, like this giraffe learning to move as a youngster, running across what is potentially a slippery terrain and then falling over. It doesn't always end up and result in injury, but it does result in a movement failure. And it's during these types of movements we can start understanding what are the different trade-offs that are occurring within them as well. So really what I'm getting at is complexity. This is one of the key words across all of these different aspects. We have a multi-layered level of complexity, right down from the basic structures, the different muscles, up to the jointed lever systems. And combining those, you end up with this highly redundant system. There's so many opportunities and different ways of performing the same movement. How do we control that? We then go even to a higher grace level and we look at the complex environment and the complex behaviors we perform, and there's even more layers of complexity. And yes, we have this high-powered machine, the brain, that's able to do so many different permutations all the time. But does it really want to or need to deal with all of those permutations constantly? Or is there potentially an area and a way that it deals with this complexity to reduce that control. And so how does this sensorimotor system enable our successful movements? And this is really the area where I'm starting to look at and trying to build on what's already within the literature. With regards to applications, these are a couple of examples, but there's a huge host of different areas this can be informative for. Our robots, our multi-legged robots are undoubtedly far more successful at movement than our bipedal one. So the lower image is of Honda's Asimo. And yes, it's outdated. We have more advanced bipedal robots, but still they have some downfalls. So whether it's a stability issue as Asimo, who cannot climb up the stairs without falling over, or whether it's the requirement of high amounts of energy to be able to perform those movements, they're still not as successful as our multi-legged robots, and particularly across uneven or non-steady behaviors. Within assistive technologies, we have a similar set of issues. And again, our technology is advancing. This is Suit X, an exoskeleton, which enables those paralyzed to be able to walk again. And this is through motors at the hips and the knees with controls with these integrated crutches. But still, the movement is very slow. It is not what you would hope to be able to provide with a better quality of life for those patients. And the same is seen within our prosthetics and our orthoses. And I'll be coming back to the orthoses later on in this talk as well. And then when we look at neurological or musculoskeletal diseases, our rehabilitation programs are successful, but they're not 100% successful. Why is that? What are we missing? And again, I will touch on it a bit more later on. Our return to play, we are able to get our athletes back up to performing their sport, but often there's a much higher risk of re-injury or potentially a different injury in and of itself as well. And so if we can start understanding the control, we can start pinpointing what elements maybe we can use to identify disease progression or reduce progression, or even look at what we haven't rehabilitated back to the pre-injury level as well. And so therefore, understanding control has a huge capacity to greatly improve the quality of life for humans as well. So what do we control? There's been a huge body of literature looking at various elements as to what could be the main control parameters within our locomotor systems. And the ones which are quite often postulated are things such as controlling the movement of the center of mass, or being able to adjust the leg stiffness to different requirements. And there's evidence for both of these. So we see center of mass movements being tightly controlled within different surface property changes, and this will be an adaptation between the surface stiffness and the leg stiffness to keep that center of mass trajectory constant. And within the leg stiffnesses as well, we see how this can be adjusted based on the different types of terrain, often by adjusting the ankle stiffness itself. And within simulation studies, it's also been shown that if we adapt the leg stiffness during the late part of the swing phase, we can increase an individual's robustness to terrain. So what I mean by that is they're able to deal with a much larger perturbation within there. But we also have evidence that, particularly within uneven terrain, these two factors aren't necessarily controlled. So within uneven terrain, this is from a paper on human participants, we see that the center of mass is adjusted dependent on the step height, often to about 40 or 50% of that step height. So we're not completely accounting for the whole of a step, but a partial amount of it. So the individual isn't keeping that center of mass steady across it, but it's also not completely adjusting that center of mass to account for the entire height of that perturbation in there. And with the leg stiffness, we do see that humans tend to use a large range of leg stiffnesses, and these are adjusted within movement, but this isn't the same for other bipedal species. For example, the birds, who also have a huge range of potential leg stiffnesses they could use. But rather than having a constant leg stiffness maintained across terrain, what we instead see is that they actively adjust the leg length by shortening it or lengthening it, dependent of what is required at the time. And I've pulled these two factors out because they've been one of the most studied across the literature. But there's been a huge host of other features which have been suggested to be part of the neuromechanical control of movement. And there's many more others that I could have mentioned, which there just isn't time for within this talk. But what I'm trying to get at is, can any of these be those key control priorities for movement? If they're used within certain scenarios but not others, the potential is that they're unlikely to be those key facets that the neuromechanical control of our systems are identifying to keep consistent. And what I mean by consistent comes back to kind of this simplification of the locomotor system, and talking about task relevant versus task irrelevant parameters. And what I mean by that is we have a set goal for each of our movement behaviors. And there will be certain parameters that will directly affect the possibility of attaining that goal, whereas there will be other parameters which, if they adjust even to a large degree, may not have any consequential effect on that goal attainment. And so this is where the idea of this optimal feedback control comes in. So parameters which are directly relevant to the task will have lower amounts of variability within this minimum intervention principle and optimal feedback control idea. Whereas parameters which are task irrelevant, so won't necessarily directly affect goal attainment, will be allowed to vary more up until within their ranges of motion if we're talking about joint angles. So there are some restrictions on them, but it's not a focused feedback control as it would be for the parameters which will directly affect us being able to attain that goal. And so therefore, if we simplify that control and allow large variability in task irrelevant, but control and fine tune those task relevant parameters, maybe this is how our neuromechanics allow us to have this task success with a relatively simple system of control. And if that is the case, then what are these parameters? Can we identify what are those task relevant parameters? And can we even say that it's task relevant across any behavior? Would there be a fundamental set or singular parameter across all complex behaviors within all complex situations that the system is controlling for? And one of the ways I'm looking at this is by, again, simplifying this locomotor system and simplifying this complexity. So that's by using these reduced order models of locomotion. So this is not a novel model. It's been used in the literature since the 80s. It's been around for a long time. But what it is basically looking at this complicated integrated neuro MSK system and reducing it down to physics, basically, using the physical limitations and understanding. And so nowadays our models are more complex. So we use actuators and dampers within this spring mass model to try and give more details and understanding to our complexity. But if we reduce it even further, so it's literally a point mass and a massless leg, we can start looking at specific parameters based on these reduced models of locomotion, and they have to sit within the physical bounds and principles. And it's from there where we potentially might be able to start understanding some of these key control parameters. So we can use this as a template potentially to understand the underlying neuromechanical control. But we also have to remember that if we simplify the system, we still need to understand the task complexity. And what I mean by that is, yes, we can use these reduced orders models of locomotion, but we need to not only understand the level terrain movements, of which we have a good understanding of, but we also need to understand those unsteady and uneven terrain movements as well, because these are the ones which will push that neuromechanical system further and make it a more difficult task to control. And so therefore complexity of that task will increase potentially what we can identify within these key control parameters as well. And this is what we see every day when we're moving around. We have to deal with stairs, we have to deal with curbs or potholes. We have complex movements just during our daily activities. And then if we add sports within it, these are even more complex behaviors and even further pushing the neuromechanical difficulty within those systems. And the ideal situation would be if we understand this neuromechanical control, maybe we can actually identify or create and design a parameter which will allow us to say whether this movement will be successful or not, or what is the risk of performing this movement within a variety of situations as well. Specifically, how I do this within my own work is using perturbations. Within this talk, the majority of the work has been done using obstacles. So I will put an obstacle within a movement pathway and get either animals, as you see, or humans to move over that obstacle. Because at this point, we put various factors into a direct conflict. So over this obstacle, do you keep that center of mass trajectory constant, or do you crouch your leg or lengthen your leg to deal with it, dependent on what stage of that process you're in? So I'm going to talk a couple of projects which I've worked on or working on, and looking at scaling and human applications, and then also how we can potentially define locomotor success, or what is locomotor success as well. So start with the scaling aspect. So this was some of the work I did at the Royal Veterinary College. And basically it's the idea of how does uneven terrain movement scale with size. So with isometric scaling, this is the proportional maintenance of shape. And from that, what we know is that weight or force scales with mass, whereas we know that musculoskeletal strength will depend on cross-sectional area. And this scales at a much lower rate at 0.66 to mass. And on top of that, the further issue is that material properties, such as the properties of bones or muscles, remain the same. So what this means is larger animals have a big problem. The bigger they are, the more stresses and forces they need to deal with. How do they deal with that? And one of the things that has been looked at is that posture changes. So what I mean by posture is if we look at the hip height, so that's H, so that's a vertical height, and then if we sum all of the leg segment lengths together, if you were fully straight, so fully upright posture, both of these numbers would be the same. Whereas the more crouched you are, the larger that sum of the leg segment lengths would be as compared to your hip height. And this has been seen within birds. One reason they also make a really good model for this is that we have a 500-fold size range within the birds, and we see this change from crouch posture to upright posture. And you can see within here that humans have a much more upright posture, very similar to those larger sized birds as well. And the reason this change in crouch to upright posture is important, the more upright you are, the more the ground reaction force aligns with those centers of joint rotation. And so therefore this reduces the musculoskeletal stresses within the system. So this is a great way of reducing that for larger animals. And so obviously they have this straighter posture, and their priority is to avoid overload injury. But is this postural change sufficient to deal with unsteady behaviors? So with my obstacle example, is this straight posture enough of a system to reduce those stresses, or do they need to adapt and differ from smaller animals how they move? So one proposition would be is, if this isn't enough of a system, what one would expect to see is that over an obstacle they may launch themselves up and change that center of mass movement to accommodate the whole of the height of that obstacle, so that they don't need to crouch and therefore increase those musculoskeletal stresses as well. And so I did this work across a whole range of different birds, right from the bobwhite quail all the way up to ostriches, and got them moving over different height obstacles. So all of the obstacles are proportional to a percentage of their leg length. What we expected to see was a difference between large animals and small animals. What we didn't expect to see was what we got, and that was that the strategy was consistent across this 500-fold size range of birds. So they all targeted the obstacle, and by that I mean on the obstacle they maintained a relatively steady center of mass trajectory, albeit more compliant. But they anticipated this by launching themselves up onto that obstacle, and on that obstacle accounted for, so there was some crouching, a partial amount of the height of that obstacle, but they never crouched to the whole extent of that obstacle. There's always a partial amount within there. And coming off of the obstacle, they literally used a very simple strategy and converted that potential energy that they'd gained going up onto the obstacle into forward kinetic energy itself. To further investigate the potential optimization they might be doing and the strategies and what this means for control, working with the robotics group out in Oregon State University, created a point mass model, but incorporating an actuator and a damper to allow input of energy or loss of energy respectively. And from that, we did a work minimization model, and we were fitting leg stiffness and leg dampening. What was really remarkable was the goodness of fits across all of this size range of birds, both within the ground reaction forces, but also within the leg actuation. So within the birds, we see this leg actuation, particularly in the second half of the stance phase. And this was replicated by this simplified model itself. And what we saw, therefore, was across this 500-fold size range was a dynamic template across all of these bird species, not just within the more crouched or the more upright bird species itself. And forces were always consistently maintained within 0.5 body weights of the level average. And so what this means is that we have a stance phase which is prioritized for safe forces, so not increasing those ground reaction forces to a large extent, and also minimum work, so minimizing the amount of work the leg needed to do. And in the swing phase, we saw adaptations within the leg swing to enable these safe landing conditions. From there, pushing it further, we started to consider, are there any parameters within this simple model that we can consider and use for potential control priorities? And simplifying this system, we have beta, which is, or I'm calling it the loading angle. And this is the angle between the leg and the velocity vector. And within this simple model, within the sagittal plane, it basically determines the amount of leg loading that will occur during the stance phase based on the landing condition. And so what that means is that at 0, it's fully loading along the leg. So therefore there is no forward movement whatsoever. As you come closer towards that 0, you're increasing the stance period and increasing the fore-aft forces as well as the loading forces. And so the closer you come to 0, the more often you do that, there is a likelihood of overuse injury associated with high forces as well. If you move towards the other end of what is feasible, 90 degrees of this loading angle, you're reducing the fore-aft forces and you're reducing the stance period, because obviously the closer you come to 90, the less of a sweep angle you're having during that stance phase itself. And at 90, you're no longer able to load the leg whatsoever, and so a stance phase is not feasible. And so therefore, theoretically, you have a risk of falling. Obviously, this depends on how quickly the other limb is able to move to counteract that as well. But there is that risk of falling associated in there. Within the birds, what was remarkable based on this simple model was that we could see this relationship between this loading angle and the leg work or the leg actuation occurring within the birds across all of these different obstacle heights as well. And what you can see here is particularly the data is much further towards the upper limits and avoiding those lower limits below the 20 degrees as well. And additionally, you're avoiding those upper extreme limits of 90 degrees also. But key here is that we have this link between the loading angle and the work output occurring within the step itself. And this is the posture-dependent actuation, which has been shown in birds, but also in humans in other literature as well. What's also really interesting is the fact that we were putting these birds onto a 50% leg length obstacle, getting them to run over it. And yet when you look at these rose plots, so basically the proportion at each of these different angle values, it's very tightly controlled across both the level but also the obstacle terrain. And you can see clearly here how those extreme values of the loading angle are avoided as well. What's also interesting to see is if you take the averages across each of these for each of the birds, the average increases as you go up in the size of the animal. So you can see that the average for the ostrich will be above 60, whereas the average for the quail will be between 30 and 60. Which, when you then consider this scaling issue of about weight scaling faster than the musculoskeletal strength, made sense, because the closer you move towards 90, the less leg loading, so the less musculoskeletal stresses you're needing to deal with, which is why that ostrich is likely sitting at a much higher average value than the other birds themselves as well. So it's interesting to see that we have a tight variability across all of these birds, but there is some differentiation due to the potential issues with scaling as well. So using all of this information, that's when I started to consider these aspects within how potentially we could apply it to humans, or is it even applicable within humans? So some of the work which I've been working on is really starting to investigate this within the human population. And as I mentioned earlier, humans have an upright posture, so very similar, say, to the ostrich. So based on the ideas we saw earlier, where we saw that shift in the average closer towards 90 for the larger birds, we would expect a similar trend within humans. And that is what we see. So this is data from a group of healthy participants who were both walking and running over level and obstacle terrain. Within the human participants, the maximum obstacle height I used was approximately 20% of their leg length for obvious safety reasons. And what was interesting to see is we still have this tight variation within that loading angle. And we do see that increased average as we would expect, say, for the ostrich, and actually pretty similar between the ostrich and the human. I should also add that ostriches weight-wise tend to be around anywhere between 80 to 100, so relatively similar to humans as well. So they do make quite a good model species for this as well. But what's more interesting is the similarities across the two. And I know I've been focusing on this loading angle, but if I suddenly switch slightly and show you something, say the knee angle at the initiation of stance and the alpha at the initiation of stance. So the alpha is the velocity vector angle from horizontal. So the alpha is, again, a parameter based on a simplified system. And again, it has this type variability. But if we then look at the knee, for example, and say in populations of ACL or knee osteoarthritis, knee joint dynamics are really important and have been used clinically for a long time. But we see a huge variability in this knee angle compared to something based on these simplified models. So if we're trying to determine a parameter where we can adjust or tweak it based on being able to inform individuals their risk, it makes it a lot harder with something with such high variability as well. And as part of that, because of this variability difference between clinical standard parameters, shall we say, and these simplified systems, I also started to investigate it within pathological gait. So here it's knee osteoarthritis. The knee osteoarthritis cohort, the level terrain is in the light grey bars on the rose plot, and the green is the 20% leg length obstacle data. What's remarkable within this cohort is the shift we see. So there is a significant difference at both level and obstacle terrain. And if you compare that to, say, both that alpha and the knee angle, there isn't such a clear differentiation as you see within, for example, this loading angle. The shift in the loading angle, moving up close towards 90 for the knee osteoarthritis cohort, potentially could be as a result of these individuals, whether they're suffering from pain and so therefore want to reduce their loading, or potentially just purely the dynamics have been adjusted to reduce that loading to potentially reduce the progression of that movement as well. These are all aspects which need further investigation as well. And moving on to kind of greater complexity or greater differentiations within sports as well, there's a huge array of different movements that are used regularly for these athletes. And one of the ones that we wanted to investigate was handstand walking. These are people using their arms. Are these arms being used as legs, or is the movement completely different? And so what we did was generated a study to test the reliability of being able to obtain this data, because this is relatively novel, and also have a look at whether things such as the ground reaction forces or the virtual leg lengths. So what I mean is that assuming a simple leg like we see in these point mass and massless leg models, are these similar to normal walking? I realise that it's confusing doing handstand walking and walking, so I say normal walking for using your legs for walking and handstand walking for when we're using our arms. And what's interesting to see was the ground reaction forces are very much what we see within running dynamics based on these models. But when you look at the potential energy and kinetic energy exchanges, So for walking, this would be an exchange between potential and kinetic energy. For running, you would see them moving in the same patterns across the stance phase. What we see was that we had the energy exchange mechanism as you would expect within walking itself. So in a perfect stylized walk, you would end up with direct transfer between potential and kinetic energy throughout the stance phase. Obviously in experimental movements, it's never 100%, and we didn't see that within the handstand walking, but we did see this energy exchange mechanism apparent within the movement. And things like the arm length, so representative of, say, the leg length in normal walking, we see similarity of patterns across from it. So there's this potential that these simple models can even inform, the more unique type movements as well, that we see across a variety of different sports. And this is an area where we're further expanding and investigating as well. So linked with these unique movements is this idea that when an athlete gets injured, we need to try and rehabilitate them back to enable them to go back to their sport, hopefully to exactly the same level that they were able to do prior to the injury. But the question is, does our rehabilitation mean fully recovered? And we know that across a wide range of different injuries, whether it's ankles, knees, hips, you name it, an injury means that you are at a higher risk of re-injury. So therefore, are we really rehabilitating them to be fully recovered? A lot of these clinical tests that are used, I would call them simple movements. So something like a single leg squat or a counter movement jump. Whereas if you actually look at the movements that are being performed within these sports, they are far more complex and likely to require a much higher level of difficulty for the neuromechanical control system. And so one study which in the process of writing up was looking at badminton players. So those who haven't had any leg injuries versus those who have had an ACL injury and then returned to play back at the same level. And these participants had to have at least be recovered for at least a year as a inclusion criteria within this study. We were looking at specifically the muscle activity within these individuals. What was remarkable was what we saw between those who have had no injuries and those who have recovered from injury. So we had a different graded response based on using clinical movements versus movements specific to that sport. So for the badminton players, that's the drop shot and the net shot, both of which you perform the main movement on your dominant leg. So if you're right-handed, it would be on the right leg, left-handed on the left leg to perform those movements. And we found significant differences between these, more often within the specific sport-specific movements as well. What was even more interesting is that this wasn't the case for all muscles. So for example, the gluteus maximus, the biceps femoris, and the semitendinosus, we didn't find those significant differences. But as I'm showing on here, the vastus lateralis was significantly different between the injured and uninjured across most of the, what I'm calling, more complex movements. And this was the same across the quadriceps muscles, which we were measuring, but not the hamstring muscles. And there is some evidence already that the quadriceps tend to be more negatively affected by an ACL injury. But what we're able to show here is specifically within badminton players, even though they've recovered and they're back to playing, there is still a lack of full rehabilitative capacity within this neuromechanical system. So there is still a loss even after this full recovery. And potentially this is the loss which may then later on down the line result in this higher risk of re-injury itself. And what we're trying to do at the moment is to combine these simplified models, these reduced order models, with the muscle activity as well. And potentially here, we can not only understand the underlying control, but also identify through this muscle activity where the specific focus for rehabilitation needs to be. Because I understand that we're simplifying the system, which is great for understanding control. But when you then want to add rehabilitation into it, you need to rehabilitate specific elements. And so therefore we need to add back in some of that complexity into that system. But what I potentially believe is that we need to consider these within behavioral contexts. And what I mean is that if you've got a badminton player, we need to think about looking at their specific badminton movements in order to understand whether there truly has been a full recovery or not. So associated with this and this element of control, and as I've been mentioning across these aspects, is can we also determine a parameter that allows us to know whether a person can perform these movements successfully, or be able to define a risk factor associated within movement? And that then comes back down to the question, what is locomotor success? Is it being able to do the movement, or is it just failing? Well, realistically, it's going to be a range. It's going to be a scale. It's going to be including, additional overuse injuries. It's going to be including falling over. There's a huge host of behaviors in between these two elements. So how do we distinguish that? And I've started doing some work with children with cerebral palsy, specifically those who use ankle-foot orthoses, so AFOs. These ankle-foot orthoses are there to help prevent the plantar flexion of the foot, or drop foot as it can be known, which we know creates issues of stumbling, and then obviously difficulty moving within more complex terrain. It also assists with the knee posture as well during movement, because the muscles around the knee are weakened, often within cerebral palsy individuals. So AFO prescription has been shown not to have changed since 2011, and there's been 3 or 4 systematic reviews since then which have indicated that the prescription is not consistent between individuals, between countries. There is no diagnostic specificity within this. And so even to the extent of, does it actually improve the gait or the movement? But then the next question will be, well, which elements are important to improve? Obviously, we want to prevent the foot dropping during the swing phase and help support the posture during the stance phase as well, to generate those forces for propelling an individual forward. But is that what is key, to be able to adjust for all of these elements? And so it comes back to, what does improvement actually mean? And I've been working with SME, Andy Amo, and basically they 3D print their ankle foot orthoses. So a standard procedure will be plaster of Paris casting, then you wait a long time for that to be refined, and sometimes so long that by the time it gets back to the child, who we know grow quickly, it doesn't fit properly. Whereas this 3D printed ankle foot orthoses, the turnaround time can be, anything up to a maximum of 2 weeks. So, it comes back faster. Additionally, they are much lighter as well. And because the morphology is laser scanned, potentially even more accurate than a plaster of Paris cast as well. So this has huge implications for the fit for the children. And what we started to do is look at, how do these 3D printed AFOs differ from, say, a standard AFO or from just walking shod with no ankle, foot or facies. And we've been using a whole host of different parameters to see what are the changes, are there changes, and how do we define relevant. So, we've got key elements such as fore-aft velocity. Within the Andiamo AFO, it's significantly higher than a standard AFO or just shod, particularly across level terrain. It gets a bit blurred when you start putting in more neuromechanical, difficult tasks. And, with the energy recovery, I mentioned that earlier. So in a perfect pendular walk, this should be 100%. Often in studies, it's around 60, 70%. But you can see within these children with cerebral palsy, it's significantly lower than that. And again, we're seeing no real patterns across all of these elements. Other ways that improvement has been measured for cerebral palsy has been spatial temporal parameters such as stride length and step width. Again, you see an increase in the stride length within the level terrain, but it gets a bit muddled again within the obstacle terrains as well. So what's relevant to these individuals? What is those key parameters that makes the movement successful? We have anecdotal evidence from these participants saying how much they love these 3D printed AFOs and they feel they can move better. But what does that really translate into when we're looking at it from a mechanical perspective instead? And so I started using some of these simplified models as well to try and have a look at what this and whether we can see any patterns within it. They will want to load their limbs less, so they'll want to stay away from values leading closer towards the zero of this loading angle. And if we move further up to 90, we're reducing that leg loading, but you're also moving towards a potential failure limit as well. What is really interesting is that it was much clearer using these parameters. So there were significant differences between the 3D printed AFO compared to this plaster of Paris AFO or just shod. So specifically within the Andiamo AFO, the movement within the obstacle terrain was significantly higher than in the other conditions. So they were trying to reduce, or their loading was reduced within this perturbed environment where the complexity increased, and there is a potential for higher forces to be occurring as well. In the level terrain, though, it was significantly lower than the others. So it begs to start considering what are these implications on these movements as well. But what was really interesting was that the variability was again quite tight and tightly controlled within all of these elements as well. So the question is, could these potentially be an answer for what we could be looking at in terms of locomotor success? And, just to give a representation of the difference between this loading angle and, for example, again, those knee angles within these situations, there isn't a clear disparity between level and obstacle terrain data in these, whereas you can start seeing some shifts by using these simplified models as well. So what I've hopefully tried to show here is, does one size fit all? So we know scaling does affect certain elements, but the underlying aspects of it are still tightly controlled and sat within these simplified model limits within it, and based on a simple idea of how much leg loading is occurring within the sagittal plane mechanics. There is a potential that this simplification can even be used within complex behaviors, which would then make it ideal for understanding areas which have such high complexity, being able to find the fundamental underlying control principles are much harder within it. And the reduced order model parameters are much more tightly controlled. So then is this potentially an insight into control, that what is important to the system is the overall leg, not individual joints themselves as well? And then if that is the case, can we then further apply it into clinical applications as well? We know that control needs to be understood so that we can improve rehabilitation, as there do seem to be hidden alterations within the system, even post-recovery from an injury. And I would argue that success potentially needs to have a measurable definition so that we can start understanding where an individual's movement is sitting within this broad range of possibilities, whether we should be concerned that they're at a risk of a fall or an injury, or whether it's just variability around a nice centroid, which has a minimal amount of potential for failure within it as well. And once we have that, it will allow us to assess across scales, across situations, and also across different systems as well. As always, none of this work is possible by yourself. So for all of this work, I would really like to thank the funders and also all the individuals who have helped me across all the different universities and projects as well. Thank you very much for listening.
Great. Thanks so much, Ola. That was fascinating. I have a million questions, but perhaps we'll open it up to the floor and see if there's any questions out there before I get the ball rolling. Excellent. I'll start off then. So maybe with, I guess, sort of working backwards. My first question, I guess, has to do with the cerebral palsy kids that you were working with. I was really interested by the comparison of with the obstacle and without, with the Andiamo versus the normal prosthetic, like normal assisted devices, and then nothing. And especially the fact that it was a lower loading angle without the obstacle, and then it, increased. So I guess my first question related to that is, where do kids like around that sort of size range of that you were dealing with, where do they normally sit? Because you had showed us adult human on there, and that they're close to the ostrich, they're like 60 or over. But where do kids normally sit?
Great question. And I don't have the answer right now with that. So this is, if what I've shown you is kind of continuing work at the moment, and that work was possible through kind of an industry collaboration grant, which was why it was specifically focused at the children with cerebral palsy. One of the projects which I'm trying to obtain funding for is understanding that variability within children as well, specifically because obviously we were looking at children from the age of 4. Their movement isn't fully developed. There is a whole host of changes still to happen that haven't occurred, and understanding how that affects the control and underlying parameters, like you say, is really important to know and understand as well.
Yeah. Yeah, because I guess I was thinking, I mean, the quail had the lower, I mean, obviously they're not as small as quails, but the quail had the lower angles. And so what I was thinking, I guess, about your comment on how they feel when they're using these. And that if they're feeling comfortable with them, then they might be willing to use more inefficient, high muscular cost kinds of strategies if they're not dealing with whatever without fear of injury, because they're like they feel confident in what they're using, and so that might lower things, that as opposed to with these other devices, or when they have nothing on their feet, they might feel like they're going to hurt themselves, and so they're being careful, and so they're loading up higher.
Yep, definitely. And the other thing to consider is these are far lighter than these plaster of Paris casts, which means you're not putting a massive weight at the end of a distal segment, so you're not changing the inertial properties of that segment as much. So potentially the reason could purely be they feel more comfortable because they're not having to swing a massive lump at the end of their legs during that swing phase, and that in itself would result in a faster movement anyway. So yeah, there's a huge host of various conditions to understand this better, kind of why there are these changes occurring within it. From a personal perspective, it's just the turnaround time and this closer fit to the individual, is undoubtedly going to be a key element within this as well.
Mm-hmm. Yeah, fantastic. That's really interesting. I hope that work continues because it's amazing. I do have another question, if there's nothing else yet. Having to do going backwards in time in your presentation, back to injury in the badminton players. And you were talking about the importance of looking at context-specific tasks. And I'm curious about if all the people who were injured that you looked at injured themselves while playing badminton, and whether or not how they injured them, like what they were doing when they injured themselves, could impact the important task to test them in.
Right. So the injuries were during badminton play. That's when their ACLs were damaged. With regards to the movement, specific movement, that we didn't record from participants. It'd be curious to know whether looking back they would be able to remember that one. But there is a significant body of literature which shows that most often ACLs tend to be torn or damaged during a fast and sudden movement, so something like a tight turn, change of direction, or a sharp stopping or acceleration action as well. So there is, this is across sports as well. So more than likely the injuries would have occurred either coming out of something like a net shot or drop shot, or pushing off to change direction to go after the shuttle that's coming towards them as well.
Mm-hmm. And then I guess related to that, I wasn't sure I completely understood what the y-axes of those graphs were. I think it was like it was an integral, I think.
Yes, it was, and normalized as well. So we used what I didn't show was we also collected walking data for these participants. And so we normalized it to the average of the walking integral across each of these activities, so that there was some form of normalization factor across it. So basically looking at how much it changed from a walking. The reason I chose the walk as the control is, my argument is that that's what we do normally in daily activity. So potentially it's more relevant to look at it as a increase or decrease from those requirements within that movement. But as you will well know, Kathleen, there's a lot of arguments within the analysis of electromyography. So it's being able to justify what you do for each situation, you
Totally.
know.
So these were integrals of the muscle signal, though. They were like RIA or something like that.
So yeah, looking at basically an idea of the muscle volume of activity that was occurring. We looked at a variety of other parameters as well, but actually the volume surprisingly came out as showing the greatest differences between the different activities and the injured versus uninjured individuals.
Yeah, it's interesting because, yeah, it would be interesting to see what the trajectory is during the course of recovery,
Yeah.
how that changes through time. Because I remember when I tore my calf muscle playing tennis, I was so tentative for a long time afterwards because like anytime I felt anything there, like any tension whatsoever, I was scared I was going to re-tear it. But it's like, I think those integrals were a little higher in the ones who had been injured versus the uninjured. And so they're past the point of the tentative, but something isn't quite right yet. So their muscles are actually having to work harder to perform the same
Yeah.
activity. So that's, yeah, very interesting.
So one of the ideas behind that is that the control behind it is lost. And so rather than having specific set of activations, those muscle synergies, that has been lost within that recovery and not been trained back to enable that more precise control. And so therefore you've kind of got lost effort
Right.
in a way. And because of it was the quads rather than the hamstrings, they are an antagonistic pairing when performing those movements. So the other reason we chose badminton players is because I play badminton, so it was very relatable to what I do as well. But the recovery from it is very much within the quads rather than the hamstrings, which therefore makes it unsurprising that you do seem to have a greater effect on the quads being lost during that recovery post ACL injury specifically. So yeah, it's an interesting area which requires a lot more investigation, as with anything.
Absolutely. Yeah. Well, I guess, I mean, we're a little past one, so maybe we should, let people go and stuff. But that was really a very interesting talk. Thank you so much. And it was really nice to hear some of the new work, some of the new work that you've been doing, and look forward to hearing some updates on some of these new cool avenues of research. So thank you.
Well, thank you very much for the invite.